Anyway, the equation now we want to solve as the standard form y double prime plus p function x times y prime plus q x y. Now, if we equal the right hand side is 0, then we know how to solve at least we know how to get the power series. And if we get just one power series, we want the second solution, we can use the formula that we talked about last time. We get the second series and the second solution. So those are solution for homogeneous equation. But if you have an inhomogeneous term, and generally a function x, so for physics, so it can be a what we call a source term or a sink term, depends on the physics, or a driving term. So, but this one doesn't depend on x. So that's the property. Okay. And assuming we have two homogeneous solutions, y sub 1, y sub 2, satisfying the right-hand side 0, satisfy this equation with the right-hand side 0. Okay. And now we want to find a general solution. A general solution usually is what we call the c sub 1 times y sub 1. So arbitrary coefficients, c sub 2, y sub 2, and plus 1, what we call a particular solution. Okay. And then this particular solution is not unique because any particular solution adding a combination of the two homogeneous solution, that is still a particular solution. So it's not unique in the sense that you can always add the homogeneous equation or combination of homogeneous solutions. But it has the uniqueness that no matter what the particular solution you found, if you found two of them, so you say yp sub 1 and then yp sub 2. So yp sub 1 minus yp sub 2 is always a linear combination. Some the a times y sub 1 is b times y sub 2. Right? It's always a combination of the homogeneous solution. It cannot be this must be the case because you can see the reason, right? Because if you substitute this difference into the operator, differential operator, then the right-hand side must be 0 because both satisfy the inhomogeneous solution. The right-hand side for both, if operator on the first one and the second one, both give you the right-hand side, the same f, and you subtract them, so that becomes 0. So this difference satisfies the homogeneous solution. And then you have at most two homogeneous solutions. So therefore must be a combination of the two. It's okay. So that give you sometimes give you just easy way to find that, because you don't have to use the method we are going to the formula we're going to derive. But if you can see a solution right away, a particular solution right away by the form of the equation and the inhomogeneous term, then you already get this without doing any other calculation. You can guess a particular solution, just by all means just use that, because that would be enough. You don't need to use other more sophisticated method to get that, because any particular solution is as good as any other, because the difference is just the homogeneous, the combination of homogeneous solutions. Okay, so but if you cannot guess that, then this would be a general method. So we assume a particular solution. So we just use y. I mean, it doesn't have to be this one, but just assume y is now two function. The coefficient becomes function. So u sub 1, y sub 1, which obviously also a function x, plus u sub 2, y sub 2x. Right? So instead of multiply by constant, we multiply by function, u sub 1 and u sub 2. And we'll find condition to restrict the u sub 1 and u sub 2. And requiring that this will satisfy the original inhomogeneous equation, then those conditions will give you a solution for u sub 1 and u sub 2. Okay, so that is the basic idea of the method. So just substitute this one and the derivative of this one and second derivative of this one into the original equation and see what happens. So what we'll do is now take the derivative, y prime. So there are two kinds of solution because there are two terms, each term had two factors. So when you take derivative, each term will give you two terms, so altogether you have four terms. So the first one, you take the derivative of the original y, so you have u1 y1 prime plus u2 y2 prime. Okay, and then the second one, the other two terms will be u1 prime y1 plus u2 prime y2. Right, and now the idea is we want to set these two terms to 0. So this would be our choice of a condition that u sub 1 and u sub 2 need to satisfy. We require that this to be 0. Okay, that's one condition. Now, because it's 0, when we take the second derivative, we don't need to take the derivative of this term. Okay, we just take the derivative of the first two terms. So again, we'll give you four terms. The first two terms will be u sub 1, y sub 1 double pi, u sub 2, y sub 2 double pi. And then the next two will be u1 pi, y1 pi, plus u2 pi, y2 pi. Okay, and so that's all we have. I mean, that's all we need. And then substitute that into the original equation, right? And the idea is when you combine that, these are linear equations, so like p times this y prime, you have p times this one, right? And then q times this one, you have q times this two. When you add that, you see that the first term all proportion u sub 1, the second term all proportion u sub 2. So you can see that let's call this the operator on y, differential operator on y. So the differential operator on y will be quite obviously we have u sub 1 and differential operator on y sub 1 plus u sub 2. Differential operator on y sub 2, this, and that. And finally, you have these two terms equals to f. Right? And now you use the fact that these two are the solution for the homogeneous solution, or homogeneous equation, so that is 0. So you require that this 2 equals to f, these two add up to f. And combining with this 2, so you have two equations, this one and that one, for two unknowns, u1 pi and u2 pi, right? You can solve for u1 pi and u2 pi, and let's write out the equation in matrix form. You don't have to for a second order equation. The matrix is just 2 by 2, which is you don't need the matrix to solve it, but obviously this can be generalized to higher order. So like if you have a third order, then the matrix will be following the same method, you have the matrix will be a 3 by 3 matrix, and then fourth order will be a 4 by 4 matrix. Then writing is like a matrix equation would help you to organize your solution in a nice form. Okay, so we could do that right now. So the equation is y sub 1, y sub 2, y sub 1 pi, y sub 2 pi, and then e sub 1 pi, e sub 2 pi equals to 0 and f. Okay. And now you can write down the solution. E sub 1 pi, e sub 2. I mean, you don't have to use the matrix to solve it. If these two equations are simple enough for your particular equation or particular solution for y sub 1, y sub 2, then you can just solve it directly. But if you use a general method, you can just multiply the inverse of this matrix on this vector, and multiply the inverse matrix on both sides, that the left-hand side becomes your what you want. And the right-hand side will be the inverse of that multiplied by this one, right? You know how to inverse two matrix. I mean, any matrix, you know how to do that, right? So it would be what we call a determinant of this matrix, right? On the denominator. What is that determinant? Say that again. I know what you mean. But I'm asking, the denominator has a factor of the determinant of this matrix, right? What is that? Last time we gave it a name. The Wronskian, right? Just the Wronskian. And then the inverse would be, the first one would be y2 pi, right? And this one would be y1. And for this one is cancel this one and change the minus sign. And this one is to change get in which of these two, change this sign. Right? Multiply 0 and f. Which is, you do it explicitly, would be Wronskian and -2 minus f. I mean, just this column, because this multiplied this is 0, this multiplied this. So only this is y2 and minus y2 and y1 times f1. We can write f in here, doesn't matter. Okay, and that should be the general case. Right. Well, it's a question. Yeah. Your textbook write it in. The textbook write it in the exercise 7.7.1. Right. So this is U1 pi and U2 pi. Then you need U1 and U2 in here. U1 and U2. So what you need is do an integration. Integrate that. So if you want, you can write it like symbolically, at least U1, U2 will be integrating x. The lower limit is unspecified because if you change the lower limit, what you do is just getting more homogeneous solution, right? Your f. Those are not changing the w. And the Wronskian, you already have a solution. So last time we already wrote down the solution of Wronskian. It's just whatever your choice of y1, y2, just change the constant of the solution. And the rest of the solution is the same. And you have a minus y2 x prime, y1 x prime, integrate x prime. Okay, and that will allow us to to substitute in this too. I mean, if you really need to write it out explicitly, that would be the form in the 7.7.1, the exercise. So we just you can write it out. So you have U1 and U2, right? U1 will have a minus Y2, and U1 have U2 will have a Y1. And then, so we can, this is positive, the other is negative. So you write down the Y2 term first, X, and then integrate over X. And then the integram with Y1 times F divided by W. I mean, your text will use S, that doesn't matter. I like to use X prime and W. X prime. And then plus a minus, because there's a minus sign here. Was it 1x? Y2 x prime, fx prime, dx prime, W. W can be a function also. I mean, if P is 0, and W is a constant, right? Remember last time we talked about that. Anyway, that is the form after you substitute this back to here. It's okay. And again, the lower limits is left unspecified. Those can be determined by the condition imposed on your question. Sometimes you impose initial conditions, so you have a y and y prime given at a single point. And sometimes you have what we call the 2-point boundary condition. So at two different points, you impose boundary condition on your solution y. So you specify either the value or derivative at 2 different points. And that will determine the limit of this one. Okay, and yeah, I'm actually out of time. Just out of time. Let's return to this next time and relate that to what later on we'll have a chapter on green function. This is one example of a green function. You can write it in the form of a green function, but that would be next time. But any question of this formula? So it's not difficult to derive that. So you can either, I mean, when you have a question, you either rederive that or remember the formula. If the formula is more difficult to remember, you just derive it. Go through it just a few lines, you can get the formula out. Okay.